to visual impairment student inclusion using digital fabrication technologies. So we try to share some collaborative development for chemistry learning support tools. So our three base outputs were regarding 3D modeling, a 3D model representation, or some concepts that we use when we learn chemistry, okay? So we can develop then a physical prototype. Then it serves us to have enough information regarding the appropriate digital manufacturing technology that we can use for reproduce this kind of tools. And in the process, we have a lot of user testing feedback. So as one of our main outputs to develop a final prototype, okay? So our first stage was exploratory processes. We're trying to build an accessible tool. That means a tool that could be used for those that are the normal vision students and the ones that have blind or low vision impairment. So the idea was to first start with exploratory processes, so we can discover the different teaching methodologies and tools that the common teachers apply when they deliver the different topics related with chemical elements. So we register the different expected outcomes that the teacher could give us different kind of information regarding those outputs. So we also grab information regarding the different tools and methodologies, the different graphics, software, exercise, and at the end we found that for the teaching process, most of them use different kind of tools that were based in the common periodic table that we all, I'm sure all of us know. So based on that, we create a 3D model that we can represent the chemical elements and link this physical and this model with a specific concept that we all know when we start learning chemistry, that it's the atom. So we want to reflect in this tool with this concept, so we can understand that the atoms and the electrons goes around a specific shell. So the idea was to develop that kind of model, and then we can, based on that, deliver a specific physical product that help us to learn and understand the different relationship between chemistry elements. So the second interaction, the validation process of this tool was related with trying to understand or validate if our idea of this 3D modeling process were helpful in order to, serve as a potential teaching process and tool. So we wanted to validate the 4 different components. If you can see here, we have a baseboard, we have some spheres that contain specific information regarding the elements. We have 3D printing labels for the subshells that have a specific information. The spheres have a specific information regarding the elements. We practically, based on information contained on the periodic table, we developed this model. So we wanted to first to validate if this kind of gaming tool could be helpful in order to understand the electronic configuration, the electrons configuration, sorry, of the elements. So we tested with teachers, first with the ones with normal vision teachers, from high school and university teachers. We separate we validate the model, but we also validate the flow in terms of how we can build a specific methodology to use this tool in order to learn the electrons configuration for chemical elements and understand the different characteristics that some elements share because of the how they are how they have a specific electron configuration. Okay, we use as a base the experimental study that was undertook by Barstick, that is related with the embossed characters of Braille alphabet. They already prove specific characteristics or features in terms of the dots, the Braille dots. So we use that information to emboss the Braille alphabet into the spheres to drop to contain information regarding the chemical elements. So at the first validation, at the second iteration, the validation processes, after we obtain 82% of the teachers that give us positive feedback regarding the model, so we test the spheres that it is going to contain the information regarding the elements, so we can the teacher could explain further the different characteristics of the electronic configuration. So for this iteration, we test the quantity of information that we could drop into the spheres. So we tested with blind teacher and blind people that could help us to understand if there was it was too much information or it was okay, and they also test the characteristics of the dots, of the Braille dots. So we ask a lot of information. We tested the different characteristics regarding the different 3D printing that we have. We use FDM printing technology. So we test the quantity of information, and we discovered the first things that we discovered here in this second validation was that we needed to place a Z-axis point of reference because of the form, because it was a sphere. They needed a point of reference in the Z-axis. So that was the first feedback. And then the clockwise reading needed also L-shape or some kind of reference. So we get feedback in order to include this L-shaped figure into the sphere so they can read it clockwise. In terms of the technology, we have a little feedback regarding some kind of wrinkles that they notice, okay? So we understood that for the other testing, we have to prove the different qualities to change some kind of parameters in terms of the 3D printing. So the idea it was to prove that the reference in the Z-axis and the L-shaped form in order to guide the clockwise reading could be helpful, and to prove the quality of the 3D printing. So the third stage was to receive this kind of feedback. So we tested, we prototype, we have 5 prototypes. So we test resolutions in terms of the FDM and also in terms of SLA 3D printing. Okay, so in terms of the resolution for the FDM, we used 120 microns, 190 and 90 microns in different. The first one it was with PLAM, and the other 2 were with ABS. So we test the material, but also the resolution that we have, and then we try also with SLA. Here we have to highlight that for the SL resin to print it, we can fully print it. That means to print all the volume of the sphere, and to reduce the time, we could add a specific form for the printing process. So we have to reproduce the sphere with 2 holes in order to reduce the time for the printing. and we wanted to test if there was a difference if we have a specific quality differences in terms of this kind of 3D printing process. What we obtain is, even though the SLA it's have more quality, obviously, and they reduce the wrinkles, the wrinkles that appear because of the printing when we use FDM. In terms of the cost and in terms of the quality, we can use FDM 3D printing with ABS in a medium resolution, a standard resolution, and it's not going to interfere a lot with the reading process. So the cost will be less, even though the SLA it turns to be to present less difficulty in terms of the reading. The FDM could be more useful in terms of the investment. That's all. Thank you.
Thank you, Naldi, for a very interesting combination of making and education, and this idea to actually